Heads up about homework and so on. I'll pass the bonus problem back here. And I guess we've got, let's see, I think homework's due on Friday. And 2 weeks from today is our second midterm, just so you kind of think ahead a little bit, 2 weeks from today. We are in chapter 13, radiation heat transfer between surfaces. Last class meeting, we pretty much spent on how to find view factors for some examples that we worked in class. So today we're going to put those into a solution for the heat transfer between surfaces, for instance, in an enclosure. But to do that, we need a couple of equations. So we're going to start out with this little example. This is chapter 13. So in chapter 13, pretty much everything is going to be, every surface is going to be an opaque surface and a diffuse gray surface. Okay, so first of all, we know what opaque means. Transmissivity, tau, is equal to 0. We recall from chapter 12 that a diffuse gray surface is one that we can say epsilon equal alpha. Emissivity equal absorptivity for a diffuse gray surface. So those are the assumptions we're going to make pretty much in this chapter 13. So we start out and look at this surface. We've seen that little picture in chapter 12. Capital G is the irradiation. That's the incoming radiation. For an opaque surface, the transmissivity is 0, so nothing's transmitted. Some is absorbed by the surface, and some is reflected by the surface. The reflected amount of the incoming radiation is rho times G. Now, because the surface has a temperature, it also has an emissive power, capital E, epsilon EB, and of course EB is sigma T to the fourth. So now we say from chapter 12, the radiosity J, radiosity is the radiation leaving a surface. The radiosity J is what leaves due to its temperature, epsilon EB, plus the reflected amount of the incoming radiation, rho times G. Also chapter 12, we recall that alpha plus rho plus tau equal 1, energy balance on a surface. Opaque surface, tau is 0. So rho plus alpha equal 1. So here's what rho is. Rho is 1 minus alpha for an opaque surface. If it says a diffuse gray surface, alpha equal epsilon. Okay, so that's where we are now. So we're going to solve this equation for G. So solve for G. And we get this. Okay. That's just an intermediate step that we'll need to get to what we want to get to. So next step is look at Q double prime, which is Q over A. Okay. And we remember from chapter 12 that Q double prime is the net radiation leaving a surface. The net means minus. So what goes out? J minus what comes in? G. Now substitute in for G from here. And this gives Q double prime And so that's our net heat flux. Or, express it in terms of Q, and rewrite it. So you end up with that expression. What's that Q? That's the net radiation heat transfer leaving a surface. Q equal the net heat transfer by radiation leaving a surface. And then back in chapter 3, we had this. They're kind of similar. Someone said, you know what? This equation almost looks as a form of Ohm's law. A current I equal a difference in voltage, V1 minus V2, divided by an electrical resistance. So this has the format of Ohm's law, where this denominator is something like a resistance. Right, we call it a surface resistance. So R surface equal 1 minus epsilon over epsilon A. The units of this are meters to the minus 2. If you want to write it similar to what we did in chapter 3 for conduction, it looks like this. EB1, J1, let's call this guy, I'm going to call it just, I'll do it this way, 1 minus epsilon, epsilon A, and this is Q. Over here, we had for conduction, they look similar, but of course they're totally different. One's for conduction heat transfer, chapter 3. The other one's for radiation heat transfer, chapter 13. When you do a radiation problem and you model it by a radiation network with resistors, don't call those guys T1 and T2. No, they're not T1 and T2. This is sigma T1 to the 4th power. So some people in a rush, they'll put T1 and T2 there. No, they're not T1 and T2. What if the surface was black? Well, if the surface is black, epsilon is 1. 1 minus 1 is 0. So for a black surface, the resistance is 0. So if black surface what that means is if the resistance is 0, you get the maximum heat flow. And that goes along with the definition of a black surface, one that emits the most possible radiation. So a black surface is the best. There's no resistance in the surface to emit radiation. Okay, now, next. Look at two surfaces. So we'll call this guy surface A1, and this guy we'll call surface A2. And they're exchanging radiation this way and this way. Okay, so we have Q, I'm going to use a subscript 1-2. The dash means between, this is the radiation heat transfer between surfaces 1 and 2. Some radiation goes from 1 to 2, some comes back from 2 to 1. This is a difference, the difference. So how much is emitted by surface 1, A1, J1? How much gets to surface 2, F1, 2? How about surface 2? How much radiation is emitted by surface 2? A2, J2. How much gets back to surface 1? F, 2 to 1. Okay. But recall chapter 13, reciprocity, A1, F12 equal A2, F21. So rewrite this. Q12 equal A1, F12, quantity J1 minus J2. Rewrite that. Q1-2 equal and you get that. And here we go one more time. Someone said, you know, that equation looks similar to Ohm's law. A current equal a difference in voltages divided by an electrical resistance. It's a different format, but it's the same concept. So I'm going to call what's in the denominator a resistance. And I'm going to call that resistance a space resistance. So now we have something called a space resistance. The units again are meters to the -2. If you want to express it in terms of a resistance, here it is. So now, if we are going to construct a network of resistances for a radiation heat transfer problem, there's two kinds of resistances. Let's say it's an enclosure. In the enclosure, every surface has a surface resistance. Okay. In the enclosure, every pair of surfaces has a space resistance. Okay. There's R12, R13, R23, so on and so forth. Okay, so let's take a simple problem to start with. Let's do a two-surface enclosure. We'll go back to one we had a while ago in early chapter 13. It looked like this. So it could be this, it doesn't matter. It could be any two-surface enclosure. That's just an example. Okay. How many surfaces are there? There's two. Each surface has a surface resistance. Okay. If it's a surface resistance, here's where I start. Surface 1, I start EB1. There's a resistance, 1 minus epsilon 1, A1, J1, Q1. Okay, there it is, just like this. Now surface 1 exchanges radiation with surface 2. Okay, a pair of surfaces. A pair. Here it is. Now, why is it called space resistance? Not because we're in orbit. It's because there's a space between the two surfaces. That resistance depends on the space between two surfaces. That's why it's called space resistance. Okay. Two surfaces, one space resistance. Okay. What do we start with? There it is right there, J1. Put the resistance here. What's the resistance? 1 over A1 F12. Got it. J2 Q12. Okay, now we're at surface 2. That surface has a surface resistance. Okay. J2 EB2 Q2 1 minus epsilon 2 over epsilon 2 A2 resistance. Surface resistance. There's a circuit now. 3 resistors. 2 surface resistances, 1 space resistance. Notice they're in series. That tells me that Q1 equal Q12 equal Q2. They're all the same. If you want to find that, you do the same thing you did over here in chapter 3 for conduction. Here's the way you played that game in chapter 3. I want to find Q12, okay. You take the two ends, EB1 minus EB2. Divided by the sum of the resistances between my 2 fingertips. Okay. Got it. So that's how you end up solving for the heat transfer. All the Q's are equal, so it doesn't matter which one you want to look at. They're all the same. Okay. Now let's take a look at, we'll make some assumptions here. Let's say for infinite plane surfaces. Here's 2 surfaces. Okay. They're separated like that. But they're infinite. That means they go in your direction and back into the board a long, long distance. And to the left and right, a long, long distance. If they were separated by a millimeter, oh, that would be close to being that assumption. Is F12 close to being 1? Yeah, real close to being 1. 0.99 something. Yeah. So infinite just means their 2 directions, x and y, are much larger than the spacing L between the 2. That's what it means by infinite planes. Well, okay, so then put that in there. So F12 is 1. Put 1 down there. All right, so if that's the case, then Q double prime Q over A equal sigma T1 to the 4th, T2 to the 4th, divided by so that's what you end up with if you make that simplification. And table 13.3 gives about 4 or 5 examples, simple examples, like this simple example. So you can look at table 13.3 and just write the equation down. But that's how you derive it from here, F12. Okay, let's take another case. 2 black surfaces. Okay, epsilon 1 equal epsilon 2 equal 1. Obviously, this term is 0, that resistance is 0. This resistance is 0. We're left with this times A1 F12. So Q12. Yeah,
Is that assuming it's in a vacuum? Our space?
Yeah, that's a good point. There's no convection. We're not looking at convection here, just radiation. So yeah, it's going to be in a vacuum for these problems. Later on, we're going to throw convection in, and then there's going to be radiation and convection. But right now, it's going to be a vacuum, yeah. Okay, we got that. Sigma T1 to the 4th minus T2 to the 4th. Very simple result if the 2 surfaces are black, obviously. Another case. This case is enclosure with F12 equal 1. If we have that case, okay, then we have Q equal you do a little bit of algebra on that down here. Let F12 be 1. Multiply and divide by A1, and you end up with this expression. Okay. Minus 1 plus 1 comes from over here. Okay. E1 divided by E1, E2 divided by E2, and so on and so forth there. We get that simple expression. Back in chapter 1, we said, this equation appears, by the way, in chapter 1. We said in chapter 1, for a radiation problem in chapter 1, you might be able to use this equation. Then we said, but only use it if A1 is a lot bigger than A2. I'm sorry, A1, A2, pardon me there, A2, yeah. A2, A1. Remember we had the small object in a large room? That was chapter 1. And we said if that guy there is real small and the surroundings are really large, then use that equation. And we said, don't worry about where it came from. We'll tell you later. Well, now it's later. Okay, we prove it in chapter 13. If the area ratio is really, really small. If it's small, this term goes to 0. The E1 goes upstairs. Epsilon 1 goes upstairs. We get that equation. So these are just some simplifications of this equation right here. Now, there's nothing simpler than a two-surface enclosure. Most of the world can't be modeled by two-surface enclosures, obviously. So now you can guess what our next step is to look at a three-surface enclosure. I'm going to put that right here. Okay, so here's my geometry. Bottom area A1, top area A2, side walls area A3. A right circular cylinder. Spaced apart by 1 meter. Diameter is 4 meters. That's the geometry. And we're given several things. Let's put down what we're given. Epsilon 1 equal 1, epsilon 2 equal 1, epsilon 3 equal 1. T1, T2, T3. Okay, let's see. Here they are. 1,000 K. 325 K. 448 K. Let's get the areas. A1 pi r squared. That's equal to A2. Got it. A3, the side walls of the cylinder. Circumference times the height. Circumference pi d, the height 1. All right, I got all the areas. Find all the possible Q's. How many are there? 6. Q1, Q2, Q3, Q12, Q13, Q32. Or if you want Q23, doesn't matter. You can flip the subscripts any way you want. Okay, 3 surface enclosure. How many resistances on the surface? 3. Every pair of surfaces in the enclosure has a space resistance. Got it. If you want the space resistance, what do you need? I need the view factors. I need the view factors. Number 1, I need the view factors. First step, find the view factors. Okay, I don't know what F12 is. I'll guess a half. No, don't guess. You can't guess. Oh, but I do know. F11 equals 0 equal F22 for sure, plane surface. So I'm going to go to figure 13.5. Two coaxial circular discs separated by a distance L, diameter D. So in there, I have L over R1, and I have R2 over L. That's what I need to go to the graph. 1 divided by 2, a half. 2 divided by 1, 2. Go to the table and get F1, or go to the graph and get F12, 0.62. Or use the equation, your choice. Go to the graph, figure 13.5, or use the equation in table 13.2. Okay, that's one. F12. I need another one, F13. Okay, F13. Enclosure law. F11 plus F12 plus F13 equal 1. F11 is 0. So F13, 1 minus F12. 1 minus 0.62, 0.38. 0.38. And I say, you know what? It's pretty apparent to me if let's see, F13, F1 to 2, F1 to 3, F1 to 3 is 38%. What about F2 to 3? Oh, it's symmetrical. Turn it upside down. I don't care. F2 to 3 is the same as F1 to 3, equal F2 to 3. Okay, I've got them. Stop. That's all I need. How many did I find? I found 5 of the 9. 9 total view factors, 3 squared. I found 5. That's all I need. I just need those 3, F12, F13, F23. Remember the rule. Every pair of surfaces has one space resistance. Here's a pair of surfaces, 1 to 3. Here's a pair of surfaces, 1 to 2. Here's a pair of surfaces, 2 to 3. Stop, you're done. Don't find them all, especially when time's a problem on, for instance, exams. Find what you need is the word. Find what you need. Okay, step 2. Now we got all the view factors. Okay, let's go ahead and get what else we need. Sigma T1 to the 4th is EB1. Let's put that down. EB2, EB3. Okay, let's put those 3 guys down. Okay, we are 56,000. Okay. 56,700. 633. And then I need, oh, here it is, 2284. So sometimes if you want to save some time, you're doing these calculations, all you do is say, move the decimal point over 1, 2. What's that? 10 times 10 to the 4th times 10 to the 8th. Oh, easy, cancel. 5.67 times 10,000. You save some keystrokes if you want to that way on your handheld, okay? Just move the decimal place over 2, 1, 2. That makes it 10 to the 8th, 10 squared to raise to the 4th power. This is 10 to the minus 8th always, so that makes life easier when you're under stress and time, okay? You don't need to put all those keystrokes in. Anyway, there they are. All right, let's get R1. 1 minus epsilon 1 over epsilon 1. Oh, black, I'll put it down here. A1, 0, that's R2, that's R3. So we know all the surface resistances are 0. Okay, R12 equal 1 over A1 F12. Okay, find all the resistances. R12, 1284. R13, 2094. R23, the same. So getting ready to solve the problem, what you do is, of course, you find everything you're going to need. I need the view factors. Why? Because I've got to find the space resistances. I've got to find the surface resistance. Done that. I've got to find the EBs because they're known. If you give me a temperature, I know EB. Okay. Next step, construct the circuit. It's a lot like what we did in Chapter 3 for conduction. We start out with surface 1. Okay, surface 1, EB1. Surface resistance connects it to what? J1. Surface resistance, 0. J1 connected to J2. Space resistance, R12. R13, R23. Surface resistance, R2 equals 0. R3 equals 0. So there's my setup of the resistors in that network. I'm going to simplify it now. Okay. Q1 comes in. What's the hottest temperature? This guy. EB1 goes in. What's the lowest temperature? That guy. Okay. He goes out, I know. Which way does Q12 go? From hot to cold. Okay. Which way does Q13 go? 1 to 3. Okay. Hot to cold. Okay. Which way does Q23 go? 3 is hot, 2 is cold. Which way does Q3 go? I don't know right now. I couldn't tell you right now. I'll find out, but I don't know right now. But I do know which way Q1 goes. And I do know which way Q2 goes. Okay, solve for all 6 Q's. They're unknown. Solve for them all. Let's take the easy one first. Q12, EB1 minus EB2, just like chapter 3, divided by the sum of the resistances between my 2 fingertips, R12. I'll write these 3 down first. Q13, Q32, okay, so let's get those 3 guys in there. Here it is, 436,700. One, 3, 260. 3 going to 2. Okay, got them. Now, let's get the other 3. That's 3 to 6. Let's get the last 3. Let's get Q1 first. If you look at the sketch, you'll see what Q1 is. Look at the arrows. Q1 comes in. What goes out? Q12 plus Q13. Let's go to node 2. Node 2, EB2. What comes in? Q12, Q32. What goes out? Q2. Q3. What comes in? 437,000. What goes out? 7,900. A lot comes in, not much goes out. That means it's going out. So now I know that's the way it goes, that way. This minus that, Q13 minus Q32. So now I've got all of my Q's. There's 6 total. You could be asked for any one of the 6. All black surfaces. This is the simplest three surface enclosure you can have. Nothing simpler than the 3 black surface enclosure. Does it occur in the real world? Not very often, of course. Not very often, of course. No, not all black surfaces. There might be 1, 2, or all 3 non-black surfaces. So that really makes things more difficult. Okay. Let's just say as a, for instance, and we'll do the whole blown thing next time we meet, but let's just say, for instance, that somebody said, no, I'm sorry, that's not black, it's 0.4. Okay, surface 1, that resistance is not 0. So, well, I shouldn't erase the whole thing. I still have EB1. 1 minus epsilon 1 over epsilon 1 A1. Oh, let's put it down here. Okay, make life easy. Okay, what's Q12? J1 minus EB2 divided by R12. What's Q1? EB1 minus J1 divided by this. What's Q13? J1 minus EB3 divided by that. Conclusion. I can't get those Q's unless I know that J. Okay, now you got to find J1. So you say EB1 minus J1 divided by R1 equal. What goes out? J1 minus EB2 divided by R12. What goes out? Plus J1 minus EB3 divided by R13. I know it, 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 I know it. Guess what you do? You solve for J1, step one. Once you get J1, now it's easy. Now it's easy to get all the 6 Q's, but you can't get the 6 Q's unless you first find J1. Makes life more difficult. You can imagine, what if 2's not black? Oh yeah, now you got 2 J's that are unknown, and so on and so forth. Life becomes more difficult as more of these guys become non-black surfaces. But we'll do a full-blown problem next time on that. So it's a good stopping point.